All right. Hello, everyone. Today I will give a presentation on our conference paper, which is um, a deep policy learning agent for traffic signal control of multiple intersections. And this conference paper based on the work with C3PO research group in UC Davis. And my name is Chia-Cheng, and I will be the paper presenter for today. Okay, and this is my outline. First, I'm going to introduce our background and motivation, and then I will walk you through our system model and the problem we want to solve. And later, I will introduce deep reinforcement learning and how we implement our centralized traffic signal controller by using deep reinforcement learning method. And then I will discuss the experimental results we got. And final is our conclusion and future work. All right, so today already over 55% of human population live in urban cities. In near future, a continued increment in the percentage of human population living in urban areas is expected. And in response to high urbanization and because of insufficient study on comparison between deep on policy and deep of policy methods in the context of traffic signal control. In this work, we design a centralized traffic signal controller with deep reinforcement learning to improve the overall throughput and reduce traffic delay. Okay, so what is reinforcement learning? Reinforcement learning is an unsupervised learning, which means it interacts with an environment without any human intervention. So it behaves in a try and error manner. And the goal of our deep reinforcement learning agent is to schedule non-conflict traffic movement, which maximize the expected cumulative reward. And in our environment, all traffic signal controllers are synchronized and operate at every time slot. For example, our agent first observes the state of a network denoted by ST, which is described by the proposed traffic flow map at the beginning of every time slot T. And I will talk about traffic flow map later. And based on the state it observed, it's going to take an action. And this action is a bit vector. And this 9-bit indicate which phases should be activated for these 9 intersections individually in the next time slot. And finally, the agent gets a reward RT that is defined by the power metric. Again, I will discuss the power metric later, which shows how well the action AT in state ST impact the network throughput and average end-to-end delay. All right, and because the conventional reinforcement learning cannot satisfy complex state description for larger traffic network, in response to this problem, we apply deep neural networks as function approximators to approximate Q values rather than using a Q table. And the difference between conventional reinforcement learning and deep reinforcement learning is the way they generate Q values. The former stores and uses table lookup to figure out the optimal Q value, but the later uses nonlinear functions to output the optimal Q value. Okay, and next, in our Markov decision process, the environment is a grid network, which is a 3x3 grid traffic network of 9 intersections. And each intersection has 4 traffic lanes. For example, as you can see in the figure, traffic lane 1 and traffic lane 5 are 2 non-conflict traffic movements, and traffic lane 3 and lane 7 are the other 2 non-conflict traffic movements. Okay, and before introducing our state, one fundamental problem I want to talk about first, which is the huge state space problem. That is, the state space grows exponentially both with increase in the resolution of the state description and with the number of traffic intersections. So we come up with the idea of traffic flow map to address this problem by describing the state using traffic flow maps. And in traffic flow maps, the state variables can be real numbers. For example, the waiting time of the head of a line vehicle. And these state variables are mapped into color map to transform the state into an image. In other words, this image encodes head of a line delay of each lane at each intersection, and also encode head of a line delay difference between any two neighboring intersections. So the novelty of traffic flow maps is that they allow the states to be described with arbitrary high resolution and capture dynamic traffic flows for a network of multiple intersections. Okay, and given the delay metric and delay difference metric proposed in this paper, we use these delay metrics to capture the flow dynamic of the entire traffic network and formulate our traffic flow maps. And these delay metrics are stored into a 5x5 metric for one single intersection at every time slot. And the structure is shown in this figure. So the orange cycles are head of a line delay for 4 traffic lanes, as we mentioned. And the blue cycle in the center is the average of 4 traffic is the average of 4 head of a line delay. And the red and the brown cycles represent delay difference with neighboring intersections. Okay, and for a 3x3 grid network, we collect delay information from 9 intersections together to have a traffic flow map. And this is one way of constructing a traffic flow map, and there may be another way of doing that as well. And these traffic flow maps encode the delay information of the traffic flow in the network as it evolves over time. And the action is represented by a vector of binary number. For example, 0 denotes east-west direction, and 1 denotes south-north direction. Okay, and in this work, we define the reward function as power metric, which is a ratio of the network throughput to the average end-to-end delay. And the idea of maximizing power for a packet switch network is referred to as CleanRock's optimal operating point, which achieves the maximum network throughput at minimum end-to-end delay. And maximizing power implies maximizing the network throughput as well as minimizing the average end-to-end delay. So this reward function is going to assign higher reward to state action pairs that have higher p-value. Okay, so what are the benefits? In distributed manner, you can have each of these distributed agents just operate locally, but they might not maximize the global reward. But our centralized agents applies the power metric, which maximizes the global reward. And it also optimizes system throughput and average end-to-end delay. And it also measures environmental feedback by more than one factor. And next, I'm going to move on to deep reinforcement learning-based traffic signal control. And the reinforcement learning algorithm we apply in this work is on policy learning, also known as SASA. And SASA is TD learning in reinforcement learning, and YT is TD target. The loss function L is calculated by getting the difference between the TD target and the current Q value. And we are interested in the loss function where 2 separate Q networks, one is main Q network and the other is target Q network, are responsible for generating the current Q value and the target Q value. And we update the neural parameter theta that optimize the loss function L. First, the partial derivative of loss function L is calculated by differentiating the loss functions here. And the gradient of the loss function can be found by this derivative function. And with this equation phi, we find the gradient and we will have a good insight of how to optimize the loss function L and how to update the neural parameter theta by using stochastic gradient descent. Okay, so right now we are able to put all things together. So as we mentioned, we use traffic flow map to represent our state as input, and we feed those traffic flow map as input into our main Q network to generate the current Q value. And the state S, action A, and next state, next action with their reward is going to be pushed into replay memory buffer for later reuse. And we sample the history data from the replay memory buffer and feed this history data into target Q network to generate the target Q value. And we get the difference between the current Q value and target Q value. This is our loss. And we get the derivative of the loss function and update our network parameter theta. Also here we apply epsilon greedy method for exploration and exploitation for action selection. And next I'm going to move on to experimental results. Okay, so first we try different reward functions. In most Atari games, one factor based reward functions are applied to measure feedback from an environment. For example, the score an agent can obtain after an action was taken. And this simple measurement may be enough to be feedback for Atari games, but in our case, due to environment is far more complicated than Atari games. Hence, neither just throughput or just average delay, such one factor based reward can help learning process. Only the power metric based reward function is able to stabilize the training process at the end. And one of the reasons could be that the power metric co-optimize two factors, which are the network throughput and average end-to-end delay. So that is why the power metric based reward has a better performance than other two. And we also compare our result with other deep reinforcement learning agents proposed in this paper. And some of them use Q-learning with CNN and with dual-ring architecture. And in this work, the proposed 2D SASA use on-policy learning with CNN and dual-ring neural architecture. Okay, and we found that the proposed 2D SASA is able to outperform other methods in terms of learning performance and average end-to-end delay, which shows that our method is more suitable for complicated environments such as a traffic network of multiple intersections. And one of the reasons for poor performance of deep Q learning could be the size of state space, since we consider a network rather than one single intersection in this work. The state space is much larger and complicated than one intersection can have. So DQN and 3DQN both applies deep Q learning, which switches among multiple policies to maximize the expected cumulative reward. By this way, although deep Q learning can get rid of a poor initial policy and jumps to another promising one, but it could mess up the learning process when the state space is huge. Okay, and we also compare with classic back pressure based algorithms, and the results show that the proposed method can have a shorter delay and fewer outliers compared to two back pressure based algorithms. Okay, and to conclude our work, the proposed 2D SASA shows that on-policy learning with dual-ring neural architecture can perform well in complicated environment. In the near future, we plan on having a larger network such as San Francisco downtown and also using the different reward functions to see whether they will have different impact on learning. And last but not least, we are designing a two-level architecture that combines decentralized controllers at local level and centralized deep reinforcement learning agent at higher level. Okay, so this is my presentation for today. Thank you for your attention.